Hey, good morning, everybody. Last time I was looking at y'all, we were talking about entropy and enthalpy, the two driving forces of the universe that makes like pretty much everything happen. We had enthalpy with an H, and that's the heat energy, right? Or like the energy of your reactants and products and whatnot. And it doesn't seem too surprising that nature tends to go towards low energy, right? Because everything that we see and everything's rolling downhill and like ending up being like less energy. Firewood burns, right? Paper burns, gasoline burns. Raw, yeah, low energy. Nature likes low energy. And the other thing that we talked about was entropy. That has the R, and the R, that's for randomness or like chaos or how mixed up things are. And nature, it turns out, likes things to be super duper messy, like really, really messed up. The more mixed up and crazy things can be, the happier nature is. So nature, low energy, super duper messy, and those are the two driving forces. Nature will drive towards lower energy as much as it can to get to as low an energy state as possible. However, entropy, the randomness, that's the force that trumps everything. Everything in nature is moving towards greater and greater entropy. Every process, like the entire universe, is becoming more and more mixed up and chaotic. That is just nature. So next time your, parents tell you to clean up your room, tell them it's not your fault. It's just, just nature. But today what I want to talk about are these. The variables that affect the reaction rate. So entropy and enthalpy like make the chemical reactions happen, but there are a few things that we can do to actually make it happen faster. You get what I'm saying? Or like slower if we do the opposite. But today we're going to look at not just what makes it happen. Now step 2, what makes it happen faster or slower if that's what you want. Now the first thing that we're going to look at is this thing, the nature of the reactants. And that's basically going to be ionic versus covalent, right? And before we talk about that, we got to remember, harken way back like 2 or 3 days ago, to collision theory. Remember, like, so for a chemical reaction to happen, the reactants got to smash together hard enough to break all those bonds and make this like explosion type like mishmash of like reactants, product, explosion, and then they snap back together and make the products if enthalpy and entropy are being obeyed. Now, remember, first part, step 1, they got to collide. They got to collide with, like, into each other hard enough to break bonds. So keeping that in mind, let's remember that reactions occur by first breaking bonds, right? First you got to break bonds, and then you got to rearrange bonds, right? So that stands to reason that the fewer bonds are broken, the faster the reaction is going to be. Okay, so that's like the thing. To get a chemical reaction to happen faster, you got to break bonds faster. You got to break the old chemical bonds faster so that you can rearrange them to make the new chemical bonds, right? So for ionic substances, they are fast, like wicked, crazy, fast, like almost instantaneous, which is why we are made out of water. Like if we put our hand on a red hot stove, not going to take much time for us to a whole bunch of processes. The nerve endings have to detect the heat. Then they have to create a signal. The signal has to go up our arm and hit our spinal cord and sometimes up to our brain. But if it's a reflex, probably not. Just into our spinal cord. There has to be some kind of weird decision. Like, is that hot? Is that cold? Is it too hot? Is it too cold? Like what? And okay, so what do we do? Okay, let's pull our hand away. So let's make that signal and send it right back down into our arm, and we got to activate after the signal gets down there. The signal has to be transferred into all the muscles and coordinated in such a way that our muscles can then contract and pull our hand off. Dude, it has to be fast, or we're just gonna cook ourselves by accident if we trip it or something into a fire somewhere. Like fast. Ionic substances are super duper fast if they are in an aqueous solution, right? If they're dissolved. And the reason being is that the bonds are already broken, right? If you have an ionic substance, it's just floating around, right? It's just floating around. The ions are already broken apart. They're just like tootling around in water, and there's nothing to break apart. They are already broken. So an effective collision for an ionic substance that is dissolved All the effective collision is they bump into each other. You don't need any, like, there's almost no kinetic energy needed, because the kinetic energy in creating a chemical reaction, that kinetic energy is used to break the chemical bonds, right? It's got to smash so hard that it breaks the bonds. Well, what if the bonds are already broken? All they got to do is bump into each other, and that's it. And so that's what happens in an aqueous solution dissolved in water. That's what aqueous means. This is a really good word to have dialed into your brain. Aqueous means dissolved in water. Well, we already talked about that a little bit earlier. So, yeah, it goes fast because the bonds are already broken. So, yeah, it's almost instantaneous. So if you see something, so here's the thing: if you see two things, like, oh, which of the following is going to be like really, really fast, and you have like NaCl and you have like C6H12O6. Well, this one's going to be super fast, like super duper fast. It's dissolved in water. Bonds broken. You dig? Now, sort of with the same idea, only on the other side of the spectrum are our friends, the covalent bonds. Now, covalent substances, you see how it starts with a C? These are, at least in this class, these are almost always going to be carbon-based. Or let's just say carbon-containing. Right? So that's like a clue. So if I look at C6H12O6, man, it's got a carbon all up in it. So it is covalent. And what that means is that when it dissolves, the bonds do not break. Like, there are no ionic bonds to break apart. So when a covalent substance dissolves, the water can't break the molecule apart. It separates one molecule from another, so you have one C6H12O6 over here and another one like over here. So the molecules are apart from each other, but like the individual atoms that make it up are still covalently bonded. So these are going to be significantly slower because the bonds need to be broken, right? So ionic substances in an aqueous solution, bonds are already broken. The reaction happens almost instantaneously, like fast. But a covalent substance, the bonds are not broken when they dissolve. So there has to be a collision that's strong enough to break those bonds. So this is going to be slower. You got it? I hope you get it. We're moving on. All right. Oh, actually, one last thing. They're like the ionic substance, covalent substance, like the nature of the reactants. There is nothing we can do about that. That just is. It just is what it is. You know what I'm saying? Just there it is. It's either fast or it's slow, and there's nothing we can do to tweak that, because we can't make something that's covalent suddenly ionic, because then it's a different thing. You know what I'm saying? But the next few things that we're going to talk about are things that we can actually adjust to make a chemical reaction go faster, like if we want it to go like, or if we want it to just like simmer a little bit. You dig? All right, so the first thing we're going to look at is concentration. This is basically like, concentration is basically a measure of how much stuff is dissolved in a liquid. So if you look way out to the right over here, like this stuff has like a lot, that's got a lot of stuff dissolved in it. Like whatever, I guess that's like too much Kool-Aid mix. This one right here, right in the middle, perfect Kool-Aid mixture. But this one, that one right there, that one's a little bit too dilute. You see how it's like, it's too thin. You can see that it's watery. So concentrated and dilute, these are relative terms, right? And basically what it means is if you have an increase in concentration, like, so if you're like way over here, right? Like if you're way over here at this guy, there are lots of molecules in there, relatively speaking, like lots. So if you pack lots of molecules in there, they're going to start like smacking into each other, because, you know, there's just lots of them in there. And so if it's more crowded, right, you're going to have more collisions, and then that way it's going to be more faster. It's just the way it is. You know what I'm saying? Like, there are more collisions when things are crowded, because there's just more opportunity for things to smack into each other. And the more times things smack into each other, the greater the chance of them hitting hard enough and in just the right alignment to make a chemical reaction happen. You guys get what I'm saying? Sweet. More concentrated, more stuff, more faster. So that's one thing that we can adjust. We can tweak the concentration. More concentration, super fast. Less concentration, less fast. Right. Next one. Oh, surface area. Right. So surface area, this is definitely something that we can like mess with. So the greater the surface area, the greater the chance for effective collisions. Right. So it's sort of like using a block versus like a squiggly line thing, right? And we kind of, I don't know if you guys learned about this, but in your small intestine, we have these little like finger-like villi, right, that are shaped like this. Our small intestines are like that. Oops. Right? And the other side has, the other side of the small intestine tube has these little finger-like projections in like that. And if you can imagine, our tubes of our digestion, like our small intestines, are shaped like that so that we have tons and tons of like surface area. Because if we just had a straight tube like this, I mean, if you look at this versus this, the one on the left there, this guy, way more surface area per like, I don't know, length than if you had something like this. This is flat, right? There's more surface area in just these two villi than there is in that whole side. So we do that so there's more surface area, so there's more chance of our nutrients to be absorbed, right? So same thing with the chemical reaction. The more squiggly and wiggly the shape is, like the more surface area you can get, the more chances for a collision. And the greater the chances there are for a collision, the greater the chances that it's going to be an effective collision, and it'll make it happen. So we have two choices. We can we can shape it in a way that's like that gives it more surface area, or the other option is we can chop it up into many little pieces. So we can have like a whole chunk versus like many pieces. And for this, the best analogy is like making mashed potatoes, because man, who doesn't like mashed potatoes? I don't know. Nobody human. But anyway, to make mashed potatoes, right? If you imagine you had a big fat potato like this big, like the outside skin is brown, but the inside meat is white, right? And to make mashed potatoes, you have to chop it up and then boil it, right? So to cook the potato. But why wouldn't you just take a big giant potato that's like this big and throw it in the boiling water? Why don't you just do that, right? That must be like less cooking. That'd be easier, right? Well, if you do that, the water will only make contact with the potato on the outside part, like on the skin where it's brown, right? But if you take a potato and you cut it in half, you can see all that white meat there, right? That's new surface area. So the more you chop that potato up into the smaller and smaller and smaller and smaller pieces, the more and more white surface area you're going to see. As long as it's white potatoes, you know what I'm saying? So, like, you're chopping the potatoes up into small pieces and then boiling it because it provides more surface area. And by providing more surface area, there's more chances for water to smack into that potato and cause a chemical reaction to happen, right? And the chemical reaction is making it from raw potato to cooked potato. Definitely a chemical reaction, right? Totally different properties. So surface area can be achieved in one of two ways. One, you can have like a squiggly surface, or you can grind it up into small pieces, or if you want it to go like, you can put it into a powder. Like powdered iron is actually kind of explosive. It's a little bit dangerous. Like I don't know if you've ever heard of silo explosions, but you can even make regular household flour like light up. You can do it with cornstarch too. All you have to do is puff it into a cloud and put a light to it, and it'll just go. You guys dig what I'm saying? It's pretty awesome. So increasing the surface area can also make it go much, much faster. This is also why we have like granulated sugar. Like you put granulated sugar in your, I don't know, iced tea and stir it up. It's great. But if you put like a solid chunk of ice crystal, it's going to take forever to dissolve. So more surface area, more faster. What's next? Let's see. Oh, temperature. Well, we all know this one too. The greater the temperature, the faster it's going to be, because you're giving the particles more kinetic energy, right? So the greater the temperature equals a faster rate, because, like the reason why it's faster is because these little puppers, wait, let me get a good color here. The greater the kinetic energy, you have more effective collisions, right? Because they're moving around faster, so they have more energy, so when they collide, they're more likely to have more kinetic energy available to break those bonds and create that activated complex, right? So a little bit of temperature can increase things like dramatically. So like 10 degrees Celsius, that's like maybe, 10 degrees Celsius. That's not a whole ton of temperature, but man, you can make things go like literally double the reaction rate. So more temperature is more faster because the particles have a greater amount of kinetic energy that they can use to break those chemical bonds. And also same thing to slow it down, you just like cool it off, right? That's why we have a fridge. We put food in the refrigerator to slow down the degradation of our food so it's really slow. Like, stuff doesn't last forever in the fridge, but it lasts a heck of a lot longer than if you like put it on top of a wood stove. It doesn't. Anyway, the next thing I want to talk about is a catalyst, and we kind of spoke about this a little bit before. The catalyst provides a different or alternate pathway, right? It lowers the energy of the activated complex. So without the catalyst, the activated complex is way up here. I don't know, 6 or 6 and 7 or I don't know. But if you add a catalyst, look how much, man, I cannot draw a straight line. It lowers the activation energy to just barely above where the reactants are. So the catalyst speeds things up. Oh, this is one other thing. The catalyst itself, right? The catalyst is not altered in the process. It just sits there. It doesn't actually partake in the chemical reaction. It just helps hold things in a certain way so that activated complex is easier made, right? So all you have to do is just bump them together. You need a lot less activation energy. Way less activation energy. And what that means is it goes forward in the forward direction faster, right? By like this much faster. However, the reverse reaction goes that much faster too, right? Because it's the energy of the activated complex that has been dropped down so low. So if you add a catalyst, the forward reaction speeds up and also the reverse reaction. So both speed up and they both speed up equally. Now, how do we know if there's a catalyst involved? Because that would be important to know that, because, you know, you got to be like, got to tell everybody everything that you're doing, and we just put it right on top of the arrow. So this is the reaction that is used for hydrogen fuel cells. It's where we get hydrogen from water. We just put up a solar panel to make a small amount of electricity. The electricity is used to split water into hydrogen and oxygen. Oxygen floats away or is put in a tank for people who need it in the hospital. Hydrogen is packed into a tank. You then take that tank of hydrogen, and all you got to do is waft it across 2 platinum plates, and the platinum holds the hydrogen right up against the platinum. Oxygen goes by, bam, converts it to water, and a little teeny zap of electricity comes out. Amazing. So the platinum here is used as a catalyst, and we put it right there on top to show that the platinum is catalyzing or facilitating this chemical reaction. It doesn't take part in the chemical reaction, but there it is. It's right there making it go faster by lowering the energy of the activated complex. I wonder what's next. Oh yeah, pressure. Pressure. Dude, pressure. Because only gases can be compressed, right? Only gases. And so what pressure does to a gas, like when you apply pressure, it basically increases the concentration. So greater pressure gives you greater concentration. And we already spoke above about what happens with concentration, right? More concentration means they're all closer together. They're more likely to smack into each other. It's more likely to cause an effective collision. And here's what happens with the gas when you increase the pressure. You can see here, like the gas particles, they're pretty far apart, right? So the further apart they are, the less likely they are to collide, right? Because they're like all spaced apart. But if you squeeze them all together, you can see like they're really close there. They're a lot closer together than they were before. I don't think you can even draw it. They're really close. So the closer they are, the more likely they are to like smack into each other and bump and collide and cause an effective collision. Do you guys get what I'm saying? So I don't know if you've picked up what I've been putting down this whole time, but it's these it's like the collisions. The more we can facilitate collisions, the faster the reaction is going to be, with the exception of whether it's ionic or covalent. Those two things we can't really do anything about. We can't really change the nature of the substance. And there's temperature. Temperature, they're going faster, they're more likely to collide, and they have more kinetic energy to convert into that potential energy activated complex. So there's that too. So yeah, that seems to be like a pattern that I'm seeing here. Yeah, you just want more effective collisions to make everything go faster. Oh. It's as if I knew. It's like I'm clairvoyant. All factors that increase the rate have one thing in common. What are they making a greater number of? Effective collisions. You guys get what I'm saying? The more effective collisions you can make happen, the faster your chemical reaction is going to be. Dig. And that's it. We are all done. We are all done. Oh, look, Calvin and Hobbes. I love Calvin and Hobbes. So to noodle this information in our head and to practice it, we're going to be looking at the speed of chemistry. That's what we're going to do. It's going to be applied to like actual chemical reactions. So the ideas are there, but we're going to apply them to chemical reactions. And I think that's it for me for today. As always, y'all have an awesome day.